All right, the next topic that we're going to take a look here in 15.4 part 2. We just finished talking about cylindrical. We're now going to talk about spherical coordinates. So spherical coordinates is very useful in describing anything that has some sort of spherical symmetry, meaning something maybe is a portion, maybe your region can best be described by a portion of a sphere, or maybe you can describe your region where things tend to be um, bounded by surfaces that are, one surface is a certain distance away from the origin, constant, compared to another, things like that. Anytime there's some sort of spherical symmetry, spherical coordinates can greatly simplify the task of a triple integral. So, here's the theorem that I have in my notes here. But before we actually use this, we are going to go ahead and derive spherical coordinates. So let's take a look over here at a derivation. So the basic idea in spherical coordinates, we're going to compare it to Cartesian and cylindrical as well, so you kind of get the full idea of what's going on. So here are our standard three-space axes, x, y, and z. And in Cartesian coordinates, if you have a point, you can go ahead and label that point with an x, comma, y, comma, z, where x, y, and z are simply the displacement from the origin in the direction of the x, y, and z axes, respectively. So let's go ahead and just give a little bit more information to this point. So let's go ahead and imagine this point, the image of this point, but onto the xy plane. So if you can imagine this point floating above the xy plane, we're just going to imagine dropping it directly down until it hits the xy plane. So if we do that, we'll have a point like this, and this point is different than this point, but it's very much related, and its coordinates would be x, comma, y, comma, well, 0. All right, now that we have that, let's go ahead and imagine a line from the origin to this point in the xy plane. Okay, so the length of this line is r. It's the exact same r in polar coordinates and in cylindrical coordinates. Furthermore, let's go ahead and label this angle here measured counterclockwise from the positive x-axis to be theta. And now we know that in 2 dimensions, a point can be listed from, or can be converted or written in terms of polar coordinates if it's in the xy plane. So this would be r, comma, theta, and if since we're in the xy plane, this would be 0. So that's our usual polar coordinates. And in fact, this point here is still considered cylindrical coordinates because, well, we've got this z. Sure, it's 0, but really, polar is the same as cylindrical coordinates if you only consider points in the xy plane. Cylindrical is just another way of meaning you have a third dimension. So it's polar plus the third dimension. So this point up here in cylindrical coordinates would be labeled similarly as r, comma, theta, comma, well, whatever the z value is. Okay. So let's do something else now. And let's go ahead and look at another line segment, but this time from the origin to the point in 3D itself. This line. This straight line, we're going to call this distance rho. So let's say rho, the Greek letter rho. And then that's the distance. And then we're going to come up with another angle here. This angle is phi. Some people say phi, some people say phi, whatever, doesn't matter. Sometimes I say one or the other. Okay. So what we have now is another way to actually describe this point. So now this would be rho theta phi. This right here is the point xyz written in terms of spherical coordinates, where this point is written in terms of cylindrical. Oop. Trying to get the right color here. There we go. And this, of course, is Cartesian. So Cartesian, cylindrical, and spherical coordinates. Now we know in polar slash cylindrical, we know that we can convert very nicely. So polar slash cylindrical, we have the following conversion factors. We have x equals r cosine theta, y equals r sine theta. We also have that x squared plus y squared equals r squared. Now for spherical coordinates, what do we have? So for spherical, we have x equals rho cosine theta sine phi, y is rho sine theta sine phi, and z is rho cosine phi. Where do we get these from? Well, we get them from the following. So first thing we want to do is notice that since this goes directly down into the xy plane, and this segment that we've labeled with r lives in the xy plane, that means that this has to be a right angle. Might not look like it, but that's due to the perspective, but this is a right angle, and therefore this is a right triangle. So it's this triangle that we actually want to go ahead, extract, and take a look at. So I'm going to go ahead and just draw that really quickly. And also notice here that this angle is phi, so that means that this angle up here also has to be phi. So, moving over here a little bit, we have a right triangle with an angle phi, hypotenuse length rho, and then this adjacent side z. All right. And this bottom side here is r. So let's also import that. so r. All right. So with this triangle right here, what we want to have now is consider what happens when we take a look at the cosine of phi and the sine of phi. Well, using good old SOHCAHTOA, cosine of phi is adjacent over hypotenuse. Solving for z, we get rho cosine phi, which is the one relationship we are after. So, done. Now what do we have with sine of phi? Well, again, SOHCAHTOA, this would be opposite over hypotenuse. So r over rho. Let's just go ahead and solve for r so that we have rho sine phi. And now we know that since x is equal to r cosine theta, this means that r, which is rho sine phi, we must have our relationship. Rho cosine theta sine phi. That's what x is equal to. Why did I rearrange and switch the order of the cosine and sine term? No particular reason, nothing important. That's just how I have it memorized in my own head, because this is x, and I know that from polar coordinates, the distance from the origin times cosine of theta is your x. So this helps me just remember the spherical formulas. That's all. It's easier for me to memorize. Beyond that, no reason. Similarly, for y, we have y equals r sine of theta. We could replace r with rho sine phi sine theta. So then we will have r sine theta, it's not r, excuse me, rho sine theta sine phi, and that's y. So those are the three relationships we had in the previous section down here. In particular, they're listed right here. Okay. Another fact that I'm not going to go into a ton of depth on right here is dv for spherical. So for spherical, dv turns out to be rho squared sine phi d rho d phi d theta. And this is all encoded down here. Right here we have our dv. This is our original function f, same as over here. But then x, y, and z get replaced with what x is equal to, what y is equal to, what z is equal to. So all the same information is encoded down here in the theorem. So this really is what you want to look at when you're doing spherical coordinates.